Hey everyone, welcome to section 3.7. This is going to be the last section that we do in chapter 3. There are a few other sections like 3.8, 3.9, but I figured this one would be just more interesting, a nice way for us to kind of wrap up this chapter. Section 3.8 is, they're all interesting, but 3.8 is about this thing called Newton's method. It's a way to find the zeros of a function, so basically like where I cross my x-axis. But there are easier ways to do it on your calculator. So I thought, let's stop with section 3.7. We're going to talk about these things called optimization problems. Basically, this section is how do I take the calculus that I've been learning and apply it to real world situations? How do I use maximum and minimum info to help me out in the real world? So it's applied math today, and our objective is one thing: solve applied minimum and maximum problems. We're going to start with our first example here. A manufacturer wants to design an open box having a square base, so all sides are equal, x and x, and a surface area of 108 square inches, as shown in this figure. What dimensions will produce a box with maximum volume? So these problems are called optimization problems because I'm trying to optimize a quantity, and in this case, that quantity is going to be volume. When we're doing an optimization problem, we start with what's called our primary equation. And this equation is basically a formula for the quantity that I'm trying to optimize. So I need a volume formula. In this case, I'm dealing with a box, so length times width times height. My length and my width are the same, x times x, my height is h. So my volume equation for this box would be x squared times h. So that's your primary equation. Again, it's primary because it's the formula for the quantity to be optimized. We also need a secondary equation because right now, one equation with 3 variables, that's not going to be super helpful for me. I want to get it down to eventually one equation with 2 variables. So to do that, you need a secondary equation. Your secondary equation, it'll change depending on the problem. In this case, they're giving it to us by telling us about our surface area. So surface area is the area of your base, x squared, plus the area of your 4 sides. So I'll write that again here. That x squared is the area of the base. The 4xh is the area of your 4 sides. And that's something that they're giving to us. They'll often give you some more information. I would trust that you would be able to figure out your surface area equation for a box. You could. Sometimes they'll ask you to figure it out. Sometimes they'll just give it to you. So those are our 2 equations, primary, secondary. Because I'm trying to maximize V, volume, I want to combine these equations up, and I want V as a function of just one variable. So what we're going to do here is we're going to recognize that S, we actually know what S is. It's 108 square inches. So I'm going to rearrange my secondary equation, and I'm going to solve it for H. I'm going to solve it for H because when I do that, I can take this new expression and I can plug it back into my primary equation for H right there. Okay, so rearrange, I have 108 equals x squared plus 4xh, and I want to get H by itself. I'm going to start by subtracting the x squared from both sides. So I have 108 minus x squared equals 4xh, divide by 4x. Divide by 4x. Okay, that's going to cancel out over here. I'm left with h equals 108 minus x squared all over 4x. So again, what we did here was we took our secondary equation. We recognized, oh, hey, they're actually giving me surface area. So now I have an equation with just 2 unknowns. I'm going to rearrange that to solve for h. And now I'm going to take this expression and I'm going to plug it back in to that primary equation up there. So we end up with v equals x squared times 108 minus x squared all over 4x. And we're going to simplify this a little bit. I'm going to distribute that x squared in there because right now it's a little messy for my taste. So we are going to separate into 2 different fractions, and you're also going to be distributing that x squared in there. So I'm going to have 108 x squared over 4x minus, distributing that x squared again, minus x squared times x squared. That's going to give me what? X to the 4th over 4x. Okay, I can simplify that a little bit more. 108 divided by 4 is going to give me 27. X squared divided by x is going to just leave me with an x. X to the 4th over 4x is going to give me x to the third over 4. So this right here is the equation that we are going to now do some calculus with. What we did again, I have my primary equation, I have my secondary equation, I rearranged my secondary equation, and I substituted in this expression for h in my primary. So now I have just v as a function of one variable. That variable is x. Okay, we're going to take this with us onto the next slide, or keep moving down on your paper. So I have v equals 27x minus x cubed over 4. At this point, I want to try to figure out what x values, right? Because that's what they're asking us for. I'm gonna go back a second. They're asking us what dimensions will produce a box with maximum volume. So we want to figure out what x values are going to yield a maximum volume. Before we do that, let's figure out a feasible domain. It does not have to be a perfect domain here, but what we're doing is we're just saying, hey, what would kind of make sense for our x values here? We know that our volume should be greater than 0, right? If I'm looking for a max, then my volume should be greater than, I guess it could be equal to 0, but that's not going to be very helpful. We know that x should be positive, right? And a negative wouldn't really make sense. So x is going to be non-negative. The area of the base, so a equals x squared, that should be at most, that should be at most 108, right? If they told us our surface area is 108, then the area of my base should be at most 108. That would give me no sides at all, a useless box. But once again, right now, we're just trying to figure out what is our feasible domain. So using all of these things, we can say that 0 should be less than or equal to x, should be less than or equal to, well, if our area, if x squared is equal to 108, then x should be less than or equal to the square root of 108, all right? And x is going to be positive. So once again, this is just a feasible domain. This is us just taking a step back, recognizing, okay, where should I be looking? What makes sense for this problem in the real world? Now we can get back into the calculus part. So to maximize v, to maximize or optimize our volume, we want to find critical numbers, find crit numbers of the volume function on this interval. So find critical numbers on this interval that we just kind of determined over there, okay? So you know how to find critical numbers. Find your derivative, so dv dx, remember that's kind of a throwback. We haven't really used dy dx, in this case dv dx, in a little while, but that just means first derivative, right? That's going to be 27, that's my derivative of 27x, and then what would your derivative of minus x cubed to the fourth be? Well, you can think about that as pulling down a 3, so you'll have minus 3/4 and then x squared. Okay, so that's your derivative. To find your critical numbers, you're setting that equal to 0. So 27 minus 3/4 x squared equals 0. I'm going to move this whole term over here, right? I'm going to add that. So I get 27 equals 3x squared over 4. Multiply both sides by 4. I get 108 equals 3x squared. Divide by 3. We're just doing algebra at this point, right? And then you're going to take the square root, so you get 36 equals x squared. When you take that square root, you get x equals the positive or negative square root of 36, which is positive or negative 6. We said that negatives wouldn't really make sense, so we're just going to say we're looking at x equals 6 as our value here. All right. We could now evaluate this x equals 6 as our critical, and we could evaluate our two endpoints, 0. So remember that, we're thinking back to the beginning of the chapter now. Because I had an interval, I have these two endpoints. I have 0 and I have square root of 108. How would I evaluate absolute max and min if I am given a closed interval? Do we remember how to do that? So remember, you would take all of those values and you would plug them into your original function. So what's v of 0? What's v of positive 6? That's your critical number. And what's v of square root of 108? If you plug these numbers back into your original function, you would get 0. If I plug 6 back into v, so I would get 27 times 6 minus 6 cubed divided by 4, you're going to get 108. And if you plug in the square root of 108, I'm not going to do the work, you can do the work for that one, you would get 0. So this is just kind of proving to us, and hopefully that makes logical sense, right? When we were creating this interval up here, we were saying, like, I just need some boundaries. It makes sense that these boundaries are not going to produce your max or your min in this case. But this process over here is kind of our double check. And we're just saying, hey, I'm trying to find absolute max and min on a closed interval. I need to take my endpoints. I need to take my critical points. I need to plug them back into my original function. So this is just proves that v is max when x equals 6. Okay. If you think about this then, your volume, right, was x squared times h. If you're trying to maximize your volume, well, we know x should equal 6. That's what we just determined. And we plugged that into our function up here to figure out when x equals 6, what is my volume? So to solve for h then, you're plugging in 108, you're plugging in 6 squared, and you're solving for h. You're going to get 108 equals 36h, divide by 36, divide by 36. We get h equals 3. So your final answer here, v is max when dimensions are 6 by 6 by 3, and all of these would be inches. That is our final answer for this problem here. So that's our first example. Pause, go back as needed. I know I'm doing some of the explaining vocally, not writing all of it down. Rewatch this example if you need. I also put the entire section 3.7 up on Classroom. They give you some other examples there. We're going to do one other example together. But once again, what we're doing here is we are taking all that we've been learning about calculus, and this is kind of a culmination point. We kind of culminated with the graphs. We got to sketch graphs, but that's all cool. What does it mean in the real world, right? Where do I actually apply this? Remember, calculus, it's the math of change. How do I use calculus in the real world? I've been trying to tell you it is useful. This is one of the ways you can use it. One of the many, many ways you can use it. So here are some guidelines. This section is in your textbook as well. This is kind of your step-by-step process here. So if you're doing an optimization problem, identify all given quantities and all quantities to be determined. Sometimes a sketch is really helpful. It's not necessary, but can be helpful, can just help you keep track of things. You're going to write your primary equation. This is a formula for the quantity that is to be maximized or minimized. If you need to, you can find some of these formulas in your textbook. Reduce the primary equation to one having a single independent variable, so you might need to use a secondary equation. Remember how we had two equations? I solved one equation out for one variable and then substituted into my primary. Find your feasible domain, so what kind of end caps would make sense. Sometimes you're not really going to be able to have a feasible domain. It totally depends on the problem, but usually you can have some kind of, educated guess about what your final answer should be. And then you're going to determine desired maximum or minimum value by the calc techniques that we discussed in the beginning of chapter 3. So find your derivatives, figure out where your maxes and your mins are. All right, one more example. Example 2, so this is just showing you a different case. This is back to a graph. Which points on the graph of this equation here are closest to the point 0, 2? So they kind of are giving you these little red dashed lines over here to show your shortest distance, and we're trying to figure out what would these potential points actually be. Okay, they're also reminding you of your distance equation down here. Hopefully that one's locked in somewhere. So your primary equation would be your distance equation, and they already plugged in this point. So I'm going to write it out generally. Remember, your distance equation is, I already messed it up, whoops. x2 minus x1 squared plus y2 minus y1 squared. Remember that from back in the day? That's your distance equation. In this case, they're saying, well, I'm just trying to find one point xy. I know my other point is 0, 2. So this is our primary equation for this particular problem. And I'll write that out over here. So that's our primary. Right now, not super helpful. I have D, I have X, I have Y. That's a lot of variables for one. So remember, you want to optimize, in this case, your distance. We want to find our minimum distance. So that's a little different than example 1. There I was finding max, here I'm finding min. Use that other equation that we have of our actual function here, y equals 4 minus x squared, as your secondary equation. And this one is already solved out for y, so we're just going to take this expression, we're going to plug it in for y over here. So we're also going to do some simplification along the way. So d is going to be, well, x minus 0 is just x. So x squared plus, over here I have 4 minus x squared, that's what I'm plugging in for y, minus 2, that's just the rest of our distance formula, squared. Let's do a little simplification here. So I'm going to get x squared, and then 4 minus 2, I can combine those up. So I'm going to have negative x squared plus 2, and that whole thing is going to be squared. I would recommend at this point actually foiling this out, because I want to kind of condense this whole entire thing as much as possible. So we're going to take a quick sidebar over here, and I don't really like that the negative x squared is first. So I'm actually going to put the 2 first over here. So I'm going to have 2 minus x squared, and because that's squared, I'm going to actually go ahead and FOIL that out. So I'm going to get 4 minus 2x squared minus 2x squared plus x to the 4th. Okay, so 4 minus 4x squared plus x to the 4th. That's what our FOILed out version of this is. We're going to plug this back in here. Stick with me, folks. I have x squared plus 4 minus 4x squared plus x to the 4th. So our final simplified version is square root of x to the 4th minus 3x squared plus 4. Okay, all we were doing there is some algebra. Okay, at this point, I am trying to optimize distance. I am trying to find my minimum distance. To do that, I want to use some calculus. So I want to figure out what would my minimum value be. I need to figure out what my derivative is going to be in this case here. So when you think about domain here, your domain is going to be the entire real line. You don't really have any boundaries here, which means I'm not going to be able to use absolute max and min. I don't have endpoints. I'm going to have to think in terms of relative max and min. So when we're thinking about our feasible domain, I have no endpoints, which, like I said, leads us to find our relative min instead of our absolute min, which means you're going to have to use some of your other processes, maybe your first or second derivative test, okay? When we think about this, if I'm taking the square root of something, well, then my minimum value, the thing inside of here, its absolute min is going to be 0, right? So what we're going to do is we're really just going to figure out, I'm just going to take that inner part out, and I'm going to say, okay, I need to figure out where the derivative of this thing equals 0. Okay. So f prime of x, and f of x I'm just saying is that inside part, right? Square root of this function would be 4x cubed minus 6x. To find max or min, remember, we're going to set that thing equal to 0. I think I need a little more space, so we are going to duplicate this slide over here, and we are going to clear it. So I had a derivative there, f prime of x, that was 4x cubed minus 6x. We're trying to find our critical numbers here to help us find max or min. I can factor some stuff over here, so I'm going to pull out a 2x. That's going to leave me with 2x squared minus 3. That's going to equal 0, so x could possibly equal 0. Or if I set this piece over here, 2x squared minus 3 equal to 0, you would get x squared equals 3/2. So x would equal positive or negative square root of 3/2. So these are going to be your two well, rather 3, right? Because I have positive and negative, your 3 critical numbers. X is going to equal 0, square root of 3/2, or negative square root of 3/2. And because I don't really have endpoints, right? We talked about that on the previous slide there. I don't really have endpoints for this problem. My domain is the entire real number line. I'm going to have to use a different method to determine which one of these values might represent the x value that will give me my minimum distance. You can use your first derivative test, or you can use your second derivative test, right? Both of those tests are helping you find your relative extrema. The way the book does it, they use their first derivative. So if you want to check that out, you can. So remember, first derivative test, you would do your little line with the arrows. You would figure out where you're increasing, decreasing. I kind of like the second derivative test better. So I'm going to do the second derivative test. Your second derivative test is find your critical points, which are right up here. We found them. Good job, us. And then plug them into your second derivative. So let's quick find our second derivative. We're going to get 12x squared minus 6. And then all I'm going to do here is I'm going to plug in these different points. So my second derivative of 0 would be 12 0 squared minus 6. That's going to give us a negative 6. So our outcome there is negative, which means I am concave down. So that would actually give me a relative max. That doesn't help me. Second derivative, plugging in that second critical point, 12 times radical 3/2 squared minus 6. Well, radical 3/2 squared is just 3/2. So 12 times 3/2 is going to give us 18 minus 6 is going to give us positive 12. So it's going to give us a positive, which means I'm concave up, which ding, 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 means I have a potential minimum. Let's test out our last one, plugging in negative square root of 3/2. Well, because you're going to square it, you're going to end up getting the same exact thing as when you plug in positive square root of 3/2. So you're going to end up with positive 12 again, which is a positive, which is concave up, which is another minimum. And that should kind of link up with what we're seeing on our graph, right? I have 2 possible points. They should kind of have mirror image x values. So we just found our x values, square root of 3/2, negative square root of 3/2. So the closest points, I'm going to put our conclusion up here. The closest points to this point, 0, 2, are square root of 3/2, comma, okay, if you plugged square root of 3/2 in over here, you would get 4 minus 3/2, which would be 8/2 minus 3/2, which would give you an outcome of 5/2. And then our other point would be negative square root of 3/2. You're going to end up with the same exact y value. So that is your final answer. So this one, it's a little different because we had to use our distance function. We had to say, well, if I have a square root, my minimum value there would be like 0 on the inside of that function, right? Like this piece inside here, I can't have that be negative. So we just kind of pulled that part out and said, that's the function that I'm going to use. I'm going to find my derivative. I'm going to set that equal to 0 and go from there. So that's how your distance problem was a little bit different than the last one. Also, we were finding a minimum instead of a maximum. So if you need to go back in this video and rewatch parts of it, if you need to read it in the textbook, or like I said, I put the section 3.7 up on Classroom, do it, whatever is going to help us understand this more. Like I said, in the video, I did second derivative. In the textbook, for this particular example, they did first derivative test. You can use either one. All we're trying to do is find our extrema here, our mins and our maxes. Use the technique that works for you. Alrighty, folks, good luck with this. Email me if you have any questions. You have a few homework problems. You got this.